This lecture is to introduce students to the concept of percent composition. 60% of the time it works every time. That's a quote by Ron Burgundy from the movie Anchorman. So we want to be able to express things in terms of percent composition. And what that means is you should be able to represent the amount of an atom present in a compound. For example, if you have CO2 minus, or excuse me, CO2, you should be able to recognize that the carbon represents 1/3 of the number of atoms in the molecule. We also want you to be able to use percent composition by mass to obtain an empirical formula. And we also want you to be able to distinguish between what's called an empirical formula and a molecular formula. There's a big difference between those two that we need to talk about. So the first thing we want to do is we want to look at what a molecular formula is. And what a molecular formula represents is it represents the number and type of each atom. So for example, you have 4 carbons, 10 hydrogens, and 1 oxygen. Okay, what you should realize is that the molecular formula does not represent the connectivity of the molecule, just the number of each type of atom present in a given molecule. And you see that with these two structures that are shown below. So you see this one right here is C4H10O, but the oxygen is in the middle of the molecule. You see this one is C4H10O, with the oxygen and a hydrogen kind of off to the side. These two compounds both have the molecular formula C4H10O, and it does represent the number of atoms that are present of each type, but it doesn't represent necessarily everything that we need to know about the chemical or about the chemical makeup. So, if you have a compound such as C4H10O6, there's lots of ways that you can express the amount of each atom present. And the first thing is you can represent the number of atoms. For example, you can say there are 4 carbons. You can say there are 10 hydrogens. And you can say that there are 6 oxygens. You can also say that carbon represents 4 out of 20 of the molecule. Hydrogen represents 10 out of 20 of the molecule. And oxygen equals 6 out of 20 of the molecule. But those things don't really represent anything of any given importance. Really what we want to focus on is the idea of the percent mass. So, you see what we talked about here. You see there are 6 atoms out of a total of 20, or 30% of the molecule, or 30% of the atoms are oxygen. Okay? Doesn't really mean anything though, so we want to get something a little bit better, and that is percent composition by mass. In order to do percent composition by mass, what you have to do is you have to find the mass of each constituent part. So for example, there are 4 carbons. Carbon has an atomic mass of 12, so I multiply 12 times 4 and I get 48. 1 times 10, because you have 10 hydrogens. 6 times 16, you get 96 oxygens. That means that the total mass of this particular molecule is 154 grams per mole. So if I want to find the percent by mass of each particular compound, I just take whatever the mass of carbon is, divide it by the total, multiply by 100, and I get 31.17%. Or I can take 10, which was hydrogen, divide by 154, multiply by 100%, and I get 6.49. And so on and so on. The key thing though is it should add up to 100%, because you have the whole molecule and you're trying to figure out what the percent by mass of each piece is, but overall it has to add up to the total molecule. So this is one of those things that you should be able to do. It's relatively straightforward, but you do need some practice with it. So let's give you an example, and this is a pretty tough example. It's got kind of a lot going on. It says thiamine C12H17Cln4OS is one of 4 nucleotides that stores genetic information in deoxyribonucleic acid. So you knew it as DNA last year, and you said that there was A, T, G, and C. And that's true. This is the T, and the T is represented by this formula right here. A lot of people think, oh, it's T, it's just one atom. It's not. It's a combination of them. It's very complicated. So it says, what is the percent composition of each element in thiamine? So in order to figure out what we need to know here, the first thing we need to know is we need to find the total mass of the molecule. So the first thing that you should do is you should look up the atomic masses. And how you do that is you go once again to our periodic table. And you look at our periodic table, and we can find the atomic mass of carbon. We can find the atomic mass of nitrogen, oxygen, anything that's on that molecule. You can find. So, for example, chlorine is 35.45, and oxygen is 15.999. So you can use those to help us figure out what the atomic or the overall mass of the molecule is. So we start off with carbon because it's first. We say we have 12.011 atomic mass units, and we have 12 of them. So that right there is 144.132. Okay, so carbon is taken care of. Next, we look at hydrogen. Hydrogen is 17, and the atomic mass of hydrogen is 1.008. Multiply that out, and you get 17.136. Next, you have chlorine, and you have one chlorine at 35.45. So that is 35.45. You have four nitrogens. So you have 4 at 14.007 or 56.028. Next, we have one oxygen at 15.9994. When you multiply that out, you get 300.805. And then finally, you have one sulfur at 32.06. 32.06. Whoops, made a mistake here. This right here should have been 15.9994. You guys are probably wondering where I got that from. Now, when you take all of these things and add them together, what you're going to get is you're going to get the atomic mass of thiamine. And the atomic mass of thiamine, when you add all those things together, is 300.805 grams per mole. That's where that 300 number came from. So now you've got this 300.805 number. What that represents is that is the total mass of the molecule. So if I want to try and find the percentage that each molecule contributes, what I can do is I would divide each one by that 300.805, and I want to do that all the way down. When I divide each one by 300.805 and I multiply it by 100 to turn it into a percent, I get the percent of each molecule. And what you get is for carbon, it's 47.92%. For hydrogen, it's 5.70%. Go ahead and put the elements out there. For chlorine, it is 11.79%. For nitrogen, it is 0.63% nitrogen. For oxygen, it is 5.32% for oxygen. And for sulfur, it is 10.66%. Now, if you were to take all these percentages and add them up, you're not going to get to 100. And the reason why is we rounded at several steps. We rounded right here, and we rounded right here when we divided. It should be pretty close, though. It should be something like 99 to 101%. And if that's the case, then we know we just rounded and we have small errors due to rounding. But like I said, this is as tough as it gets because you have so many different molecules that you're trying to keep track of. Most of the ones that you do are going to be much, much easier than this when we do percent composition. So, an example of the next one, it says, what is the percent composition by mass of oxygen in barium sulfate? So one of the things that you have to know in order to start to solve this question is you have to know what the formula is for barium sulfate. And the formula for barium sulfate is BaSO4. Okay, both barium, which is 2 plus, and sulfur, which is 2 minus, balance each other out. So you have barium sulfate. So now, what is the percent composition of mass of oxygen? And so you have to figure out what the total mass is. So you start off with the idea of barium. You have one barium, and barium has an atomic mass of 137.327. And once again, the reason why I got that number is I came here to the periodic table and I looked at barium. And barium is down here, it's element 56, and it is 137.327. So, we come back here, we have 1 barium at 1 times 137.327. We have 1 sulfur at 32.06. And we have 4 oxygens at 15.999. And we can multiply those out. And when you do that, you get an atomic mass of 137.327, atomic mass of 32.06, and an atomic mass of 63.996. When you add all those up, what you'll do is you'll get the atomic mass, or the formula mass, for barium sulfate. In this case, the atomic mass of barium sulfate is 233.353 grams per mole. So that represents the mass of 1 mole of barium sulfate molecules. So now what I can do is I can find the percent composition of each. And in order to do that, we divide each piece by 233.353. When you do that all the way down and multiply by 100, it'll give you the percent by mass of each particular compound. But in this case, I'm only interested in oxygen. So oxygen, 63.996 divided by 233.353 equals, you would get a value of 27.41% oxygen. Okay, so once again, you've got to find the total mass of the molecule. Once you have the total mass of the molecule, you divide the total mass of the whatever you're looking for. So the total mass of oxygen divided by the total mass of the molecule. One thing that gets people tripped up is they say, well, oxygen is 16, I'll take 16 and divide it by that. No, it doesn't work that way because you have 4 oxygens. So, another example that we have is, what is the percent composition of sodium in sodium sulfide? So you need to know what this is. Sodium sulfide is NaS, but this is a charge of +1, and this is a charge of -2. So the actual formula is Na2S. Okay, that right there is the balanced chemical formula for this. So next what we need to do is we need to say, okay, what is the percent composition of sodium in this? So I have 2 sodiums, and sodium is 22 point, I think it's 22.989, but let's take a look. 22.989. Okay, so 22.989. And then you have sulfur, which is 32.06. So when you multiply that out, you're going to end up getting something along the lines of, should be somewhere close to 46. Okay, we can usually round whenever we're doing these because you don't have to take it quite out that far. And this usually is something around the lines of 32. So when you find the total mass of these particular molecules, a single sodium sulfide molecule has a mass of 78 grams per mole. So if I want to know what the percent composition of sodium is, okay, I have to take 46 and I have to divide it by that 78 number. When you take 46 and you divide it by 78, and then you can't forget to multiply it by 100, you end up getting a percent of about 58.97%, which means the rest of it, the sulfur, has to make up the rest of it. It should be something like 41.02%.